I'd like to welcome everyone to the special session on quaternions at the 2021 Joint Mathematics Meetings. Our first speaker is going to be Johannes Familton, and he's one of the co-organizers, along with myself, Chris McCarthy, and Terrence Blackman. And Johannes Familton is going to be speaking on Olinde Rodrigues' most famous work. And I'd like to extend a special welcome to all our colleagues from the United States and around the world who are attending our session, and especially to our colleagues from New Trends in Quaternions and Octonions who are coming to us mostly from Europe and I think Portugal. So big welcome to them. All right, so
okay, let me just try to get this going. Okay, I have to figure. Okay, wait 1 second.
Hello, welcome to my presentation on Olinde Rodrigues.
Did you see it? I can't. I'm having trouble. I'm having problems. I'm having technical problems. I'm trying to do it. I'm trying to do it. There are too many it's too hard. Okay. Video. Okay, here's the video. Okay, now do you see it? Do you see my Olinde Rodrigues thing?
Hang on a second. I see you. I don't see your video yet.
Okay, I have to get. That's what I'm having problems with. Okay, I have a problem doing this sometimes because I can't find anything. Now, where are we? Okay, let me try this again. Share screen. Okay. Olinde. Okay, now I have to start this now. Start. Okay. No, okay, 1 second.
When you share a screen, you can choose application.
Yeah, but you have to do the timing right. That's the whole problem, and it doesn't work very well.
Did you send me your presentation?
Is it going now?
Community College, which is part of CUNY.
Do you see it now?
And this is being done for
yes, it's fine.
JMM Mathematics Meeting. Myself, and I'm from the Borough of Manhattan Community College, which is part of CUNY. And this is being done for the JMM Joint Mathematics Meeting in January 2021. The name Benjamin Olinde Rodrigues is familiar to physics students through his formula for power series coefficients of Legendre polynomials, produced early in his life. In fact, he discovered these polynomials in 1816 before Legendre did. Rodrigues published only one other scientific work 24 years later in 1840. This was a monumental and exhaustive study of mathematics of rotations and translations of a rigid body in 3 dimensions. This preceded Hamilton's discovery of quaternions by 3 years. Although Rodrigues was a prominent man of his time, his scientific work has been sadly neglected. His 1840 paper may be considered Rodrigues' most famous piece of scientific work, yet in the 178 years since its publication, except perhaps for excerpts, it has yet to be translated into English as a full transcript as far as we know, and his priority over other discoveries of the formula for Legendre polynomials was not recognized until 14 years after his death in 1851. Dr. Lucio Prado and myself started translating Rodrigues' 1840 paper in 2017, but never completed the task. Dr. Richard Friedberg, one of my former advisors, has now been translating the entire paper. I have been intimately and continuously involved in the process of the translation. Through this process, we have uncovered just how deep and self-contained this paper is. In this talk, I will discuss Rodrigues' 1840 paper. I will also give some of the insights that I and Dr. Friedberg have discussed and discovered as a result of struggling through this paper in its original French form, and how it can be compared to Hamilton's work on quaternions. Hamilton discovered quaternions in 1843 after a long algebraic study. Soon afterwards, he realizes that rotations could be described by quaternions. This geometrical discovery was eventually published in 1850 with the title On Quaternions and the Rotation of a Solid Body in the Proceedings of the Royal Irish Academy. But Hamilton wasn't the only one, nor the first, to think about rotations, about a fixed center. Leonard Euler, Olinde Rodrigues, amongst others, also thought about them. In 1840, Olinde Rodrigues published a paper on rotations. He published this paper in French. In English, this would translate to On the Laws of Geometry that Control the Displacement of a Solid System in Space and the Variations of the Coordinates Producing this Displacement, considered independently of any causes that produce it. Rodrigues's paper was important for several reasons. He departed from Euler by considering only the geometry of motions, kinematics, without regard to the physics that produced them. He describes general motion as a composition of rotations and translations. By doing this, he showed that these combinations form a non-commutative group. He preceded Hamilton's formula for a biquaternionic description of rotations by 3 years before Hamilton even discovered quaternions. He introduced a set of parameters from which rotations can be calculated by purely rational operations. This has become indispensable to present-day computer programmers. The 60-page treatise consists of 2 complementary parts. In the first part, he gives a complete description of all possible displacements of a rigid body, starting from first principles using only geometrical reasoning. In this part, there is not a single displayed equation. In 2 or 3 places, an important quantitative law is presented entirely in words rather than symbols. In the second part, he rederives all the results of the first part using only algebraic methods and appealing to them to geometry only for such basic principles as the Pythagorean formula for distance in terms of rectangular coordinates. In both parts, he lays stress on the fact that when 2 rotations are performed successively, the result may depend on the order in which they are performed, only not if the rotations are infinitesimal, but that the order of successive transformations does not affect the result. In each part, he shows how to determine the composition of 2 displacements. In the algebraic part, he shows how to describe an arbitrary displacement by 4 real parameters, 3 of which define a pure rotation and the 4th a subsequent translation. In the final part of the treatise, he explores the philosophic contrast between geometry and mechanics using many detailed algebraic arguments. In the course of his paper, Rodrigues supplied a proof to the theorem by Euler on the motions of 3 dimensions with a fixed point. Rodrigues's proof is essentially the same as Euler's, but in Euler's proof, it is surrounded by other material such as what we call today Euler angles. We shall use modern vector notation to describe what Rodrigues did. Rodrigues' composition theorem of pure rotations about an arbitrary origin of coordinates O. Let alpha L hat mean a rotation through W and angle about the axis L hat. Let beta M hat mean a rotation through an angle about axis M hat. Let gamma N hat mean a rotation through an angle about axis N hat. Rodrigues was able to prove that the composition law, gamma N hat is equal to alpha L hat, beta M hat. These are equivalent to the following formulas.
So instead of saying them,
These are the same formulas that arise from the multiplication of two quaternions. We can illustrate this as follows. We let the quaternions QL, QM, and QN equal the following, where the quaternion product is QN is equal to QL, QM. We work this out in the following way.
So we calculated this out algebraically.
And found that indeed this is the same formula that Rodrigues got without the use of quaternions. Deriving Rodrigues' rotation formula from Hamilton's biquaternion formula for rotation. Here again, we use modern notation. We derive a biquaternionic formula for rotation. Given a unit vector n hat in 3 space and an angle theta, we want a formula that can be applied to any vector v to obtain the result of rotating v about n hat through an angle theta. We shall call this result v prime. For any vector w, we shall write w in square brackets for the quaternion IWX plus JWY plus KWZ. Then for any W and W prime, we have the following. And we'll call this equation 1. In particular, we form equation 2, where n hat square bracket v vector square bracket is equal to the following, which is the dot product and the cross product in modern notation. Likewise, v square bracket n hat is equal to the following dot product plus the cross product. So we call the first one equation 2 and the second one equation 3. For future reference, we noted that when we subtract these two, we get 2 square bracket. Given a unit vector n hat.
Should I go back for it? Wait a second here.
That's fine. It's okay.
QL. Here again, we use modern notation. We derive a biquaternionic formula for rotation. Given a unit vector n hat in 3 space and an angle theta, we want a formula that can be applied to any vector v to obtain the result of rotating v about n hat through an angle theta. We shall call this result v prime. For any vector w, we shall write w in square brackets for the quaternion IWX plus JWY plus KWZ. Then for any W and W prime, we have the following. And we'll call this equation 1. In particular, we form equation 2, where n hat square bracket v vector square bracket is equal to the following, which is the dot product and the cross product in modern notation. Likewise, v square bracket n hat is equal to the following dot product plus the cross product. So we call the first one equation 2 and the second one equation 3. For future reference, we noted that when we subtract these two, we get 2 square bracket n hat cross v. We let the vector w equal n hat cross v and w prime equal n hat. In 1, we have the following. Replacing the v square bracket in 3 by n hat v, given by 2, we get the following n hat v n hat. Given theta and n hat, we now form the unit quaternion, and we call this equation 7. And its conjugate Q star, and we call this equation 8. We propose the rotation formula as follows, and we call this one equation 9. We have then QV equals to the following, and so we get, after some calculations, the following. Equations 4 and 6, this becomes the following. Where we have Q, V, and the conjugate of Q is equal to this equation 11. From this, we recover the formula for V prime. And this formula is the well-known Rodrigues rotation formula that Rodrigues found by direct geometric arguments. It is attributed to his 1840 paper, although we were unable to find it explicitly. It should be mentioned that this formula is independent of the Euler four-parameter formula that partly inspired Hamilton's discovery of quaternions. The Euler formula requires a constraint on the parameters equivalent to a restriction to the unit quaternions, and it is often referred to as the Euler-Rodrigues formula. Comparing Hamilton and Rodrigues. As mentioned earlier, Rodrigues showed how to describe an arbitrary displacement by 4 real parameters, 3 of which define a pure rotation and the 4th a subsequent translation. The 4 parameters that Rodrigues uses does not correspond to the 4 components of quaternions. Quaternions represent rotations combined with dilations, whereas Rodrigues does not allow for dilations. On the other hand, quaternions do not represent translations. The only domain of overlap between Hamilton's quaternions and Rodrigues's rigid displacements of a solid is the description of a pure rotation. And even here, Rodrigues's parameterization differs from that obtained from quaternions. Rodrigues's concerns were geometric and analytical mechanics. He did everything in the real field. He did not even consider complex numbers. Rodrigues and Hamilton came to the same conclusions about rotation, but they took very different paths. However, they both arrived in a common place using half-angle formulas. Cayley and Rodrigues. As mentioned earlier, in 1846, Arthur Cayley acknowledged Euler's and Rodrigues's priority describing orthogonal transformations. In letters to the editors of the Philosophical Magazine and Journal 13, he wrote on certain results relating to quaternions. Cayley credits Rodrigues with his use of half angles in his transformations. Cayley refers to Rodrigues's 1840 paper, mentioning that Rodrigues's results were equivalent to Hamilton's quaternions. As mentioned, Euler, Rodrigues, and Hamilton were not the only ones to think about rotations. Here is a timeline from 1840 to 1845 that includes some other people who contributed to this subject. In 1840, Rodrigues was 46, and he wrote on the kinematic description of solid movements. In 1840, Kasman, who was 31, wrote his theory of tides. In 1843, Hamilton, who was 38, wrote his algebra of quaternions. In 1844, Hamilton, at 39, wrote his biquaternionic rotations, which he finally published in 1850. In 1844, Grassmann at 34 wrote The Theory of Linear Extension. In 1844, Eisenstein at 21 wrote The Non-Commutativity of Linear Transformations. In 1844, Boole at 29 wrote the first paper on symbolic logic. In 1845, Cauchy at 56 wrote about the non-commutativity of permutations. In 1845, Cayley at 24 wrote on 2 by 2 by 2 hyperdeterminants. Thank you very much. I hope that you enjoyed this talk. Now it's time for any questions that you may have.
Okay, so that was the finishing up of the second part of what I did this morning. I did the first part where I described that my advisor, my former advisor, Richard Friedberg of Columbia University, who I've known about, I think it's about 40 years now. And we decided that after Lucio Prado and myself started translating the paper, we decided that, well, he started translating, my advisor started translating the paper. We ended up translating the entire paper. And it took us about 9 months to do it, but we finally did it. And this is a sort of summary of what we learned and what we discovered when we were translating this paper over the past 9 months that we have been working on it. So.
Does anybody have any questions? I have a question.
Sure.
Have you found a place to publish the translation? Because I think that would be something very important.
Yeah, we've been looking into that. I mean, because we also said that it's not that easy to do. We brought it up and because it's a historical thing, and it seems like things like the history of math or the history, we also had a similar issue with the history of physics, because we did some other things in the history of physics and Clifford algebras. And we've also had a difficult time finding places where this stuff is applicable. So I'm kind of reaching out if anybody has any suggestions on where some of this stuff can be published, because I have a pile of different kind of things and, different, in both physics and mathematics, not just translations, but also on the history of math and the history of physics as it relates to quaternions and Clifford algebras.
One of the publishers at this meeting is the Green Lion Press, and it seems to specialize in books about history and translations like that.
Oh yeah, you're right. I remember seeing their table at one of the other JMMs. They produce very nice things.
Down. I put down a pen and I forget where I put everything. Okay, Green Lion Press. Oh,
yeah, that's a good suggestion.
Yeah, really. No, that's one of the reasons I did this too, because we've spent so much time doing a lot of this stuff. This is what my former advisor and I've been doing, that, it would be nice to be able to publish some of the stuff we've been working on over the last number of years, which include, as you've seen, translations and then historical analysis of how different aspects of quaternions, Clifford algebras, etc., are connected. And we just have a whole collection of stuff, but we're not sure where to publish it.
Okay.
Thank you very much. I wrote that down.
Are there any other questions? They're going to throw us out at 2 p.m., which is Eastern Standard Time, which is like in 1 minute. So I guess that's it, unless there's another question. We're going to be, please come back for our afternoon session.
Yes, we're going to be here, and hopefully everyone's technology will work.
Hopefully. Just one thing I want to say is that Jonathan's advisor, Richard Friedberg, a professor at Columbia, was a student of Sungdao Lee, a Chinese Nobel laureate. And
this is true.
He's the one who discovered the so-called weak force, the weak interaction, and got the Nobel Prize for it. So he's a a grandson of a Nobel laureate.
Good job.
Yes, yes, this is true. This is absolutely true.
Living in California, TD is in California now. He's about 91 years of age. He has a son in Los Angeles. And
yes, I know. Yeah, Richard has kept me in touch. I've asked. Yeah, he's still. He was born 1926, as I recall.
Right. And the Yang is in Tianjin, outside of Beijing. He's 97. And last week I heard from a friend from Temple saying that he has a baby. I don't believe it. At the age of
Wow.
I think it's a joke.
Well, oh yeah, right. That boy, that's pretty vigorous.
Yeah.
Kevin Lambert just gave a very good suggestion that we contact David Wilkins at Trinity College. Thanks a lot, Kevin.
Okay, so we're on a lunch break now.
Yeah, I guess so. Does anybody else have any comments? Oh, by the way, Lucio Prado is here. He was the one who inspired this original translation. Lucio, would you like to say hello? Are you there, Lucio?
Yes.
Would you like to say hello, show yourself?
Absolutely.
It was because of you that this translation actually came into being. And in the beginning of this paper, I mentioned you as remember when we started this translation in 2017?
Yeah.
Now it's done.
I'm happy to be here with all of you. Sorry, my voice here.
That's okay.
Yes, it was a pleasure to work with you, Familton.
Oh, well, it's always a pleasure. As I said, I apologize that Richard Friedberg took over our task. We finished it. It's done. There's nothing more.
No, it's not going. It's research. Research is part of it. Exactly. But I'm very glad because you participate. We participate in the ICM, right?
Exactly.
Together.
This is actually from the ICM where I just kind of added stuff. If you notice, there were certain slides that were very similar to what we did in the ICM.
Absolutely.
When I added things.
So all this is adding to the new, the perspective of the history of the topics. And I think you did it pretty good. You put it together by bringing it, the old language used by Rodrigues. And,
we did the
Quaternions in modern way. Even so, actually, you need to update both the Quaternions and the Rodrigues formulas. So this is requires some work, interpretation, what Rodrigues is talking about. It's not very simple because his perspective, as you said, is oriented in the geometry and the physics. So which is the many of the explanations of the theorems are based on it. So this requires a lot of energy.
It did.
And the language he used in that time. So it's not a very simple transition. So it requires a lot of time. It's not only the French is involved, but it's
no. It's the interpretation. I mean, we took
it's
about 9 months.
That was slowed down a lot. It requires a lot of energy to get it through to the modern way, in putting, in clear way what is going on, what's the connections. I think you did a pretty good job here.
One more thing I want to mention that may happen next year is we're going to start translating his doctoral thesis, but I don't know how much it has to do with quaternions. It's more about Legendre polynomials. So we actually we got the French paper and we got some letters from about his physics. So we're going to be
he is very oriented in that. There's a very weighty on this part of all the papers that you see. This is since this is the concepts, the way you're interpreting, the way you express the concepts.
It's a lot of work.
Very important part. It's not simply the Google translation. It's not.
No, absolutely not. I mean, we meet with each other for 2 hours a week, and we worked on this for about maybe almost a year. we worked on.
Yeah, well, I remember the time you worked before the ICM.
And then we also had our trends so that we
we need to work very hardly on the boards to see the connections, the way the formulas can express, can connect each other in meaningful way, physically, mathematically.
Well, thank you.
Terrence, did you want to say anything before they?
Yeah, I was going to thank everybody.
No, I think we're good. I think we're perfect. We'll be back in an hour. Is that it?
I think it's 2 hours.
2 hours.
2 hours.
Yeah,
I
we'll
think
be back
4.
in 2 hours.
I think it's about 4.
2 hours?
Yeah.
Okay.
Okay.
Yeah.
Well, thank you everybody who's left, who's still here for being here. We really appreciate it, and please, I hope to see everybody, this afternoon, and that everybody's technology is working well this afternoon. Okay.
Of Quaternions.
Okay. All right. I'm rolling your. Hang on a second. Hang on one second.
And Octonions in physics. Okay, my name is Sultan Catto, and I'm from the CUNY Graduate School. In New York. Okay. During the past few decades, we witnessed a renaissance in the interaction between mathematics and physics. A rich cross-fertilization has been forged between them, which continues mainly between relativistic, classical, and quantized field theories and the theory of complex manifolds. So in terms of mathematics, in mathematics, we have the so-called real number systems. We call them one-dimensional structures. We have the complex number systems. Two-dimensional structures. In terms of quadratic norm division algebras, we could not ever discover the three-dimensional version of these. But the quaternions were discovered in 1840 by Hamilton. So we usually designate them with an H like that. Quaternionic numbers in 4 dimensions. And then came in the hands of Cayley and Graves within a few years later, from a few months to a few years, by say 1845 or so, octonions appeared, the so-called octonionic numbers in 8 dimensions. These are the only quadratic normed division algebras that exists in nature. And there's a famous Hurwitz theorem, which states that all the quadratic norm division algebras are real, complex, quaternionic, or octonionic, and no more. And that came in, this is in 1840, this is about 1845, and that's around 1898. So it takes another 50 years or so to develop that theorem. Okay, that's in mathematics. In physics, on the other hand, we have Newton's work on gravitation, on gravity, that appeared in early days, and then we have Maxwell's electrodynamics. Electrodynamics. That's around 1860 or so. So these were the only 2 forces known to us all the way until the early 20th century, when Einstein developed special and the general theories of relativity. So Einstein in 1905, okay, special theory of relativity, and in 1915, okay, general theory of relativity was built. And with the use of the field concept coming through the Gauss's earlier work, Einstein tried to unify gravitational field with the electromagnetic field theory. So that was to be called unified field theory. But he spent all the way until he died in 1955, practically 40 years trying to unify these two fields together, but was not successful. And the gravitational force, acts only between massive bodies. It's an attractive force. And the electromagnetic force is between electrically charged objects, such as like protons, electrons, etc. Either they attract each other, or like two like objects, like two protons or two electrons, they repulse on each other. So their equations look slightly different than each other. But after Einstein died in 1955, two great scientists, Sung-Dao Lee, okay, who was one of my old teachers, and also the lecture you heard before, he was a student of T.D. Lee before me, Familton's work you heard about, and the Chen-Ning Yang. Okay. Two great Chinese scientists around 1955 to 57. Okay, they developed what's known as the weak force, a completely new force, and that force was that force predicted the existence of some particles that were not known, and then Madame Wu, one of our old teachers, discovered those particles, but the Nobel Prize went to Li and Yang in 1957 for that work. Anyway, sometime later in 1964,
Okay.
1964,
On the left side,
okay, Murray Gell-Mann,
happening now on the left.
okay, and independently, George Zweig, okay, discovered what we call today quarks.
Okay,
And they showed that inside the bags that we call protons, neutrons, etc., there are all these entities, the smaller entities called the quarks, and the forces between them are far superior to any other force we know in nature. And then further works coined them.
Tell me what you see.
So weak force, let me underline that became as the strong force. Okay, strong forces in nature.
Okay, but you're not able to sign it.
So far in nature, we have the gravitational force. Okay, we have electromagnetic force. Okay. We have the weak forces. Then we have the so-called strong force. Okay. So now Einstein's dream to unify the two went into unifying four forces, and these are the only forces we know of today in nature. Okay, so those are the four fundamental forces. The last three of these are described by group symmetries based on special unitary groups that we call SU3 and SU2 and U1 groups. Okay. And a quest went on to unify all the forces. There's no group that describes gravity yet. And so what was finally found was this group SU5 that contains SU3 cross SU2 cross U1 internally. Okay, that became known as grand unified group or grand unified force expression. And the other work was done in that area was Gursey, my advisor. Let me mention his name. There's Gursey, who was the Gibbs professor at Yale, and his students, they developed and applied the groups that are based only on octonionic number system. These are known as G2, F4, E6, E7, and E8 on the classification of the groups. Well, it turned out that sometime later, Gross and Wilczek discovered what's known as heterotic strings. Heterotic string theories, okay, based on E8 cross E8. Okay, and of course, one of the E8s splits into SU5. It contains SU5 internally, which contains SU3 cross SU2 cross U1. So that's the so-called granulified part. The other E8 was, is it possible to unify gravity into this E8? Okay, it did not work out. So this generated a lot of hope in the 80s and 90s, the E8 cross E8 heterotic string theory, but nothing really gave any results. Anyway, so in moving towards these unification principles, we attempted first to develop some string theories. That was name given by Pierre Ramond, who was one of my advisor's students, and he is now at the University of Florida. And then we came up with the supersymmetry, which united together with the strings became known as superstrings, but no unification still exists all the way to our present day. Okay, it turned out that one of the main problems was that all elementary particles and radiation theories, etc., we work with, are all based on statistical models describing interactions in nature. They are divided usually into two groups. One group is known as Fermi-Dirac statistics, okay, built by Enrico Fermi and perfected by Paul Dirac statistics. Okay, and the particles that obey these statistics are known as fermions. Fermions are such things like protons, quarks, electrons, neutrons, etc. And there was another type of statistics that was developed by Bose and then perfected by Einstein. And it has to do with what we call the spin degrees of freedoms, actually. Statistics, and particles obeying Bose-Einstein statistics became known as bosons. So if there is going to be some kind of a unified field theory, then statistically they have to be understood in terms of their statistical phenomena by some combination of Fermi-Dirac statistics with Bose-Einstein statistics. Is it possible to mix the so-called fermions and bosons with each other? And that was really a unification idea, pushing us towards the so-called strings and superstrings and so forth, which became known as supersymmetry. So that attempt led into what's known as supersymmetry. And supersymmetry is nothing but trying to put the bosons and fermions in some kind of a structure that is able to relate all their properties into each other. So these works started with Gelfand and Lichtman in Russia first, and followed by Volkov, Akulov in the early 70s, and then culminated in the hands of West and Zumino. So sometimes it's known as West-Zumino supersymmetry. But none of this ever gave any fundamental results in nature. And then myself and my advisor Gursey, okay, we developed what's known as dynamical supersymmetry in nature. Okay. SUSY is supersymmetry. It's a supersymmetry. That's how supersymmetry is written. We related the bosons and the fermions to each other. We predicted the existence of multi-quark states, and then they were, well, Gaussier passed away, but they were discovered after he passed away. So that now we know that existence of particles with a more number of quarks in them, rather than just having quark anti-quark or 3 quark pairs in bags. We have now bags with 4 quarks, and then they move to one end of the bag and to the other. They form diquarks and so forth. So we developed that whole thing, and then that development was based on what we call the color algebra, which is based on split octonionic units, and then we wrote papers on the so-called split octonion algebra and so forth. So those papers go back to the early 80s, and I must have published like 40 or 50 works on that area ever since. Okay, so I have like about maybe 5 more minutes to talk to you. So in the remaining minutes, I will give you some historical notes or talk in the history and application of the quaternions in physics. In late 1860s, about maybe 1869, 1870 or so, Maxwell wrote that the invention of calculus of quaternions is a step towards the knowledge of quantities related to space, which can only be compared for its importance with the invention of triple coordinates by Descartes and others. And the idea of this calculus, as distinguished from its operations and symbols, are fitted to be the greatest use in all parts of science. Those were the words of Maxwell. So between 1843 to maybe 1873, Hamilton wrote his lectures on the Lectures on Quaternions. That was followed by the works of a mathematician named Tate. So first let me put the work of Hamilton on his Lectures on Quaternions, and the work of his student and a colleague Tate, who kind of took over that whole school. He wrote a treatise on quaternions around 1867 or so. And in 1873, Maxwell crowned his fundamental equations, known as Maxwell's equations of electromagnetism, from which everything you want to know about electricity and magnetism comes in a quaternionic form. In 1870, while teaching electromagnetism at Yale, Josiah Willard Gibbs, GIBBS, extracted the vectors from the quaternions. Okay, so the so-called vectors came about, and there was feuds between the school of following Gibbs and the school of Tate, but after Tate died in the early 1900s, that the old quaternion school dwindled away, and that's why we study the so-called vectorial forms these days. Okay, and then Clifford, along with Riemann, envisioned matter as, well, first of all, a related key development occurred with the introduction of Clifford algebras. Okay, so let me mention it, Clifford algebras. Okay, so that's around 1882 or so. Making the works of Hamilton and Kasman synthesized together, making the quaternions relevant in dimensions higher than 4 and giving an explicit contraction of Kasman's anti-commuting numbers with vanishing squares. And Clifford, along with Riemann, envisioned matter as a manifestation of the curvature of space and time, and foresaw some novel applications of hypercomplex numbers to the really real world that we have, the natural world. Between 1911 and 1925, complex quaternions became the basis of relativity. Number theory of quaternions became created in the hands of Lipschitz, Hurwitz, Wedderburn, Study, Dixon, and others. And these were extended by works of Aleks Kleyn and Lanxus, and a bit later by Oppenheimer, Laporte, and Eugene Wigner. And between 1927 and 1950, we saw further developments in the hands of Werner Heisenberg, Paul Dirac, Erwin Schrödinger, Max Born, and Pascual Jordan. And between 1950 and 75, this is the age of high-energy physics, when symmetry principle and Lie groups assumed a dominant role in classified particle states, leading into numbers of new discoveries. And from 1978 practically to present day, we found the natural occurrence of real quaternions in the solution of unified gauge theories and in quantum gravity. And maybe to make some mention of some names like Young and Mills and Bellevin and Stephen Hawking and future Cauchy-Riemann equations, works of Kähler and the Kählerian manifolds and hyperkähler and twistor spaces, and works of Coxeter, Atiyah, Penrose, and so forth. I think I just filled exactly 20 minutes I was allocated to, so I will stop exactly here. This is exactly 20 minutes long, okay? I did not really get into octonions, which is the area that I'm an expert in, but maybe in some other day we will give you a talk on that. Okay, thank you very much for listening, and I will take your questions if you have any now. Thank you.
Okay, can you hear me?
Yes, we can. I can hear you fine.
Okay, if you have any questions, so please, I'm here to answer anything you have. Okay. Does anyone have any questions?
So perhaps just to ask about the heterotic string theory, how does that compare to, the current sort of version of the string theory?
Oh, okay. Well, there are many different types of string theories that we have, and the part that was really more important to us was so-called heterotic string that came about some time ago, E8 cross E8, because we were hoping that one of the E8s that breaks into an E6, which contains SU5, which is SU3 cross U1 cross SU2. That's the strong, weak, and electromagnetic interaction that's called the grand unified group. So we were hoping the other E8 might contain gravity in it so that it can combine everything together, which is to be called theory of everything. So in that respect, it did not work, and we went into other types of strings. All types of different type of strings came about, and then we went on to, the further developments beyond the strings. So I think now slowly mathematics is going to move us in slowly some other directions. So, maybe away from the strings. So I don't know if that answers your question to some degree.
So I know you said the Octonions you didn't have a chance to talk about.
Yeah.
Do you want to say just 2 minutes about Octonions?
Yeah, I'll say something for 2 minutes. Now, in nature, the entities that are made out of quarks are usually bags that are made of quark anti-quark pairs, or bags with 3 quarks in them. But these bags are spinning. So when you take a bag with 3 quarks in it and you spin it, you can show mathematically that of the 3, even if they are all the same masses, 2 of the quarks move to one end of the bag and 1 moves to the other. So therefore, if there's a supersymmetry between these things that we call fermions and bosons, fermions are 3 quark, the bosons are the quark anti-quark systems. So the quark anti-quark system is going to be related to the quark diquark system. These 2 quarks form a diquark in one end of the bag. And there's no way of explaining it unless you go into Octonion algebra and build what we call, we build a split Octonion algebra, which does all the transformations in a very beautiful mathematical way. And from that, we are able to predict the masses of these diquarks and this and that. And then it leads, of course, into multi-quark states. And those things were observed just recently in experiments. So it's really a very a beautiful application, only coming through octonions. No other algebras can account for it, because non-commutative and non-associative algebra, unlike the other algebras, and it has all these beauties in it. But not only that, but I should also mention that all types of ancient geometry, starting with Pappus and the Sagues and so forth, all the way up to our date, you can map them all onto each other in terms of octonionic units. And they also allow you to understand what's going on in outer space, like how you can observe the stars with respect to each other by assigning octonionic numbers to the stars and so on. So this application has not yet been put out, but soon, talking with astronomers and astronomy people, hopefully will put out something on it. So there are really all these really beautiful geometric constructions coming out of Octonions. It's a really incredible subject. And much more than everything else, yeah.
Does anybody have any other questions for Sultan? Okay, did you have a follow-up question for Sultan? Hello, Kay? I guess not. All right, then. Thank you so much. That was an excellent presentation. Our next speaker is Zachary Hilliard from the College of Charleston, and he's going to be speaking to us about quaternion-valued solutions to the KdV equation, non-uniqueness and tail behavior of a one-soliton solutions. Okay, go ahead.
All right, thank you. So my name is Zach Hilliard, and I'm a grad student at the College of Charleston. And like he said, I will be talking to you about quaternion-valued solutions to the KdV equation. So to get started, I want to talk a little bit about the history of the KdV equation. So initially, solitary waves were discovered by an engineer named John Scott Russell, who was sitting on his horse one day along the Union Canal in Scotland in 1834. He was watching a boat be pulled in the harbor, and he noticed that a wave was coming off the ship. But unlike the waves on the beach, this one didn't lose its shape and it actually translated at a constant speed. He was able to determine this because he followed it for a couple miles and realized that it really wasn't changing. He called this a wave of translation, and now we refer to them as solitons. Later on in the 1800s, mathematicians Dietrich Korteweg and his student Gustav de Vries developed an equation to understand this phenomenon. Now, this is a nonlinear partial differential equation that they actually rediscovered, but luckily for them, they were able to obtain the namesake for it. And the equation is as follows. So we take our solution u and its t derivative and set it equal to 1/4 its third x derivative plus 3/2 u times its x derivative. Now, this is an interesting PDE because it's integrable, meaning that we can find all of its solutions explicitly, even its soliton solutions. That's not common for most nonlinear PDEs, and it allows us to really look further into the structure of our solutions. Now, we can also extend this PDE to take solutions in a non-commutative setting, and a natural generalization for this is down here. We use this generalization to work with quaternion-valued solutions, which we will be doing for this presentation. So I'm continuing the work of John Cobb, Aleks Kasman, Albert Cerna, and Monique Sparkman, who published their work last year in the Journal of Nonlinear Math and Physics, and presented their work last year during this special session at JMM. Now, they studied both rational and n-soliton solutions. Now, an n-soliton is, you can have a one-soliton, which is one solitary wave that translates through space, or you can have a two-soliton, which is two of those disturbances traveling through space, or 10, or 100, or 1 million. The nice thing about KdV and the non-commutative analog is that, once again, we can write the formulas for these n-solitons explicitly. Now, here we're working with real variables x and t, but we're working with quaternion valued functions. So we're essentially just working with a function that we can express like a quaternion, but each of the components are simply functions of the real variables x and t. Now, we're also going to be only considering one soliton solutions, and those solutions can be built using this formula for u, where we take 2 times a function phi's x derivative times its multiplicative inverse, and then we take the derivative of that product. And phi is represented here, where alpha and beta are any quaternion valued constants, and lambda is a complex number. The previous research was able to determine that no solutions to QKDV, which is what I'll refer to as the non-commutative analog, are lost by only considering lambda to be a complex number. They initially decided to use lambda as another quaternion, but found that you can make a simplification by taking lambda as a complex number. Another thing that they determined was that both the real and imaginary parts of lambda can also be greater than or equal to 0 without losing any solutions to QKDV. So that's a pretty nice simplification that we can take when trying to work with functions like this. Now, there's two main types of solutions that we can have to QKDV. The first one is a breather soliton, and that is a stationary, or we have a localized disturbance in the center that translates either to the left or to the right at a constant speed. But as time goes on, the solution expands and contracts in what looks like a kind of breathing motion. The second kind of solution that we have is a translating periodic solution, which is depicted below. What we can see here is that it essentially just looks like a handful of periodic functions that are that will translate to the right always at a constant speed. And what we're looking at in these graphs are just the component functions of our quaternion plotted on the same axis. I'm going to hop over to Mathematica really quickly just to give you an animation of what this kind of breathing motion looks like, so you can there's a little bit better of an understanding of what that means. So as we see, as time goes on, the solution in this case translates to the right, and we have this expanding and contracting motion that gives it the kind of breathing name. The translating periodic solutions, there's not much going on there. The name kind of says it all. It's just a bunch of periodic functions that translate to the right at a constant speed. Now, the type of solution that we are able to obtain also only depends on the choice of lambda. Lambda is very important. It determines the speed of translation through space. It also gives us the type of solution that we're going to experience. So if the real part of lambda is 0, then we'll end up with a translating periodic solution. If the real part of lambda is non-zero, then we'll end up with a soliton solution. If the imaginary part of lambda is 0, what we end up with is still a soliton, but it doesn't breathe. It just translates through space, and it always goes from right to left. So in any other case, we have that we will end up with a breather 1 soliton. Alpha and beta just determine the kind of structure of the different components of our breather solitons. So one of the things that you can tell pretty easily is that you can actually take two phi functions that aren't equal that will produce the same solution. So if we take two phis, we'll call them phi and phi hat, with parameters alpha, beta, alpha hat, and beta hat, and the same lambda, still a complex number, with a non-zero product. The reason why we need a non-zero product is because if one of our parameters is 0, it will end up with a trivial solution. The previous researchers were able to completely classify and understand trivial solutions, so we're just going to ignore that case for now. As I mentioned previously, lambda controls the speed of propagation. So if we were to have phi and phi hat with two separate lambdas, with our previous restrictions on the real and imaginary parts both being greater than or equal to 0, we had two different lambdas. They would travel through space at a different rate, and they could actually travel in different directions. So clearly, those are not the same solution. So the only really restraint that we have on our parameters is that we know that lambda has to be the same for both phi and phi hat. Now, if we construct phi by simply taking alpha hat and beta hat to be a real scalar multiple of alpha and beta respectively, we can clearly see that from our formula for U hat, because we can factor out the R and R inverse, we have a very nice cancellation. But what we end up with is we have our original formula for U. So clearly we have two phi functions that are different that map to the same solution. So what we were trying to understand was what is the complete classification of phi functions that map to the same one soliton solution. Now, to answer this question, we were able to develop a set of algebraic equation whose solution could potentially yield the complete classification in the case where U is equal to U hat. Now, if we consider phi and phi hat as before, and U hat defined as before, if we set U equal to U hat, we can develop the following equations. The first one is pretty simple. We can actually expand out this formula for the solution U to be in terms of phi inverses, and their x derivatives. And if we evaluate that at x equals 0 and t equals 0, we end up with the following relationship on sums and differences of alphas and alpha hats, as well as with their products with lambda and lambda squared. Now, this expression is a little bit complicated, so what we decided to do was we decided to get rid of that x derivative to simplify it. To do so, because we're dealing with functions of real variables, integration and differentiation work exactly the same. So we just integrated our formula U equals U hat with respect to x. Now, clearly, whatever's on the inside of that x derivative is going to differ by only a constant, and that's a quaternion valued constant. So if we evaluate phi x and its inverse as well as its hatted counterpart at x equals 0 and t equals 0, we come up with the following relationship. It's similar to what we had before when we were dealing with U and U hat, but still a little bit more simplified. We have sums and differences of alphas and betas, as well as along with their products with lambda and their inverses. So the next thing that we decided to do was, if we wanted to get rid of some of those terms, we could evaluate the limit as x approaches infinity of our expression phi x phi inverse minus phi hat x phi hat inverse at t equals 0. In doing so, the only terms that survive are alpha, lambda, and alpha hat, as well as their inverses. So we end up with the relationship that our constant has to be equal to alpha, lambda, alpha inverse minus alpha hat, lambda, alpha hat inverse. And similarly, if we evaluate the limit as x approaches negative infinity, we come up with a very similar relationship but in terms of betas and beta hat. Now, putting this all together, we have, if we set up our expression like we had before with alpha, beta, alpha hat, and beta hat, and lambda, once again with a non-zero product, we have that the following relationships must be true. So we have this first one that comes from our solution U and U hat, but also the more interesting one is our relationship that involves C. Since we're dealing with the same constant, we're just manipulating it in different ways. All three of these quantities have to be equal to each other. Now, myself nor Dr. Kasman are algebraists, so there's nothing about any of these equations that really jumps out at us and screams that they either can or cannot be true, or that there is some special relationship between all these parameters. So if there's anything that you see that jumps out at you and tells you that tells you something interesting about these equations, please feel free to let us know. We would really appreciate it. So the next part of our project was to understand the tail behavior of these solutions. One of the biggest classifications of a soliton solution is that the end behavior as x approaches plus or minus infinity, our solution U must tend to 0. But as we all know, that doesn't necessarily mean that it has to be equal to 0. So in order to understand this behavior, we decided to normalize the solution by taking our solution U and dividing it simply by its length. The result was pretty interesting. We actually end up with a set of periodic functions on the left and the right-hand side around the localized disturbance. So here in the middle of our graph is the localized disturbance, but on the right and the left, we have these different periodic functions. Now, the first question that we wanted to answer was, what are the equations that actually model and give us these periodic functions? By expanding U and coming up with a simple formula for its length, we essentially took a fake limit and we looked for the terms when X was much, much greater than 0 that would still stick around and wouldn't tend to 0. We did that for the both X much greater than 0 and X much less than 0. And we were able to develop these two expressions for those periodic functions for the right side of the disturbance and the left side of the disturbance down here. Now, just two notes on the notation. We have these stars attached to some of the alphas and the betas. Those just denote the quaternionic conjugate, where you invert or you take the negative of the vector part of the quaternion. The other thing is we have this -2 lambda 1 I. Lambda 1 is just the imaginary part of our complex number lambda. And the last thing is that we have this real constant h down in the denominator. So the next thing that we wanted to see was, or understand was, are the left side and the right side ever equal? As we saw in the previous, or that example, was that the left side and the right side were clearly not equal. They didn't look anything like each other. In some cases, they look very similar, but they're not necessarily the same. So we wanted to understand when the left-hand side and the right-hand side would ever be equal. So by setting the expressions equal to each other, expanding out the complex exponentials using Euler's formula, combining like terms, and factoring out our sines and cosines, we were able to use the linear independence of sine and cosine in terms of real variables to come up with the following following equations that must be satisfied in order for the left-hand side and the right-hand side to ever be equal. Once again, we're not algebraists, so these equations don't ever scream to us that they should or should not ever be true. So once again, if you've seen anything that is blatantly obvious, please feel free to let us know. So now this leads us to the remaining open questions we have for this project and also just in general about this subject. The first one is, can these equations for the equality of solutions ever be solved explicitly to yield a complete classification? We had a hunch about what we were trying to look for, and we were able to come up with some restrictions for when it would be true, but we weren't ever able to prove it explicitly. Similarly, can the equations for the equality of left and right periodic functions ever be solved explicitly as well? And another interesting question that we had was, in general, with soliton theory, the right side of the soliton and the left side of the soliton can actually look like different solutions of KdV. So a question that we came to was, do the periodic functions that arise from normalizing a breather 1 soliton ever correspond to a normalized translating periodic solution to QKdV? At this point, we didn't have enough time to look into this question any further, but it's still an open and interesting question. And the last two questions are, we realized as we were trying to understand the interaction between in a 2 soliton collision, we needed to know if what that classification was between 1 soliton. So how can we use that to further understand this interaction? Thank you all very much for your time. I really appreciate it. And if you have any questions, please feel free to let me know.
So can I ask a question?
Yes.
I was wondering for this particular PDE, could you characterize it? Maybe I missed this, but why is it natural that, you know, a quaternionic solution should arise?
So the reason in terms of this equation, or just in general, sorry.
You know, in terms of this equation, what's special about this equation that causes this?
It's not. There have been, it's not necessarily special to this equation. You can extend other PDEs to take forms in a non-commutative setting. It has to do with the Lax equation that goes along with KDV, where we can extend the non-commutative analog to the, or we can expand the commutative version to take solutions in a non-commutative setting. This one is a little bit special in the sense that it's relatively simple. So you only have, the reason why we choose this this generalization is because of we're kind of essentially adding a factor of the commutator to take those solutions.
All right. And in terms of getting the solutions in the non-commutative setting, did I get it right? There's some sense of guessing a form which has a quaternionic component to it, and then figuring out what that quaternion component looks like.
In terms of like developing the solutions, so
you had some an exponential form there. I mean, is there some guesswork going on to get that?
Yeah, so in the previous work, they were able to come up with a formula that actually would take any, you don't have to necessarily have this kind of form. You actually, what you need is what they call a KDV Darboux kernel, which is a function that the third x derivative is actually equal to the t, or the fourth x derivative is equal to the t derivative, and the second derivative is a scalar multiple. It lies in the span of any of those functions. They were able to, if you're dealing with like a handful of these functions, there's a way to build solutions based on like quaternion valued matrices and Chen determinants. But the main way that they kind of came up with this expression to find a one soliton solution was by using KDV Darboux kernels, and this was just a very convenient expression for a function of that type.
Okay, thanks.
Thank you.
Okay, our next speaker is Terrence Blackman from Medgar's College CUNY and from the Institute for Advanced Studies at Princeton. And he's going to be talking about spectral correspondences for mass waveforms on quaternion groups. Go ahead, Terrence.
All right, thank you. You know, it's a very good morning to all, and you know, it's an honor and privilege for me to speak in this context today. And let me begin by certainly expressing my deep gratitude to Professor McCarthy and Professor Familton for the invitation. This morning, I want to speak broadly on the arithmetic and geometry of quaternion algebras and on aspects of the spectral theory of automorphic Laplacians. So what I will try to describe in some sense are new spectral correspondences between spaces of mass forms on the unit group of a quaternion algebra and spaces of mass forms on a nicely related congruent subgroup of the modular group. These correspondences are predicted by the Jacquet-Langlands correspondence, and this work is joint work with Stefan Lemurel of Chalmers University in Sweden. And I've added the subtitle, you know, why is n gamma 012 nu lambda of co-compact type, in part because this is the question that has motivated our work, and it's still an unanswered question. And perhaps one more thing, I want to say at the outset, I'm going to, when I rush, I get a bit nervous, so I'm going to try to be leisurely and allow myself a little moment to kind of walk around, and I hope that you can forgive this if I don't go as fast as you expect. So, as is always the case, now, just give me one sec. So my as is the case, so my it's completely frozen. Ouch. So I now have annotation capability, but I don't seem to. Just give me one sec. So I'm going to stop the share and start the share again, and hope that that allows me to get into the share. Okay, so as is always my practice, often like to, very few people know where Medgar Evers College is, and so I'd like to say a few words about Medgar Evers College. It is, you know, I grew up here. I worked here for almost 28 years. I started in the fall of '93, and I think today, perhaps my appropriate ode to all of the things that we've been seeing today. It's named after the slain civil rights leader Medgar Wiley Evers. It's in central Brooklyn, and it's one of the senior colleges in the City University of New York. And one of the things that, you know, my now almost 30 years of experience at Medgar Evers as a faculty member in mathematics has taught me that, you know, if we're genuinely serious about the challenge of you know, developing more scholars from underrepresented communities, that really what we want to do is to sustain sort of research communities in these areas. And so in that spirit, I want to tell you a bit about sort of the research that I've done. So the structure is some broad motivating historical ideas. In particular, I wanted to say a word about spectroscopy and about this problem of hearing the shape of a drum. Then I want to talk some about what we've proved. And then I want to, if there's enough time, I'll give a sort of outline of the proof, and then maybe some speculation. Perhaps at the end of the talk, I'll share a link to the paper which I'm referring in this context. So first, I want to say something about spectroscopy, and this is Auguste Comte. And around the middle of the 19th century, this French philosopher, Auguste Comte, speculated that knowledge of the chemical composition of stars would be forever beyond the reach of science. And so he said, you know, we understand the possibility of determining their shapes, their distances, their sizes, their movement, whereas we would never know how to study by any means their chemical composition or their mineralogical structure, and even more so the nature of any organized beings that might live on their surface. Scarcely a decade later, after Comte made the statement, the new science of spectroscopy was born, and with it, the ability to determine the chemical makeup of stellar atmospheres. You know, this development precipitated a revolution in physics. The second most abundant element in the universe, helium, was first discovered spectroscopically in the solar atmosphere. And eventually an enormous database accumulated, permitting the identifications of molecules in interstellar space by the extraordinarily indirect means. Observe the natural vibration frequencies of the system, or to borrow a sort of metaphor from acoustics, observe the pitches at which the molecule rings. And once the set of vibration frequencies of the system, and this is called its spectrum, has been determined in the laboratory, then the information can be applied to astronomical observations with spectacular consequences, right? Chemical elements in stellar atmospheres could be identified by the characteristic spectral fingerprints. So the key questions that emerge are, you know, from the knowledge of the structure of an atom, how can we predict the discrete set of vibrations of the frequencies of the system. And conversely, given the spectrum of a vibrating system, what can we infer about the system structure? And I'll note here that the development of quantum mechanics was in part motivated by a need to provide a kind of theoretical underpinnings to these observations. So the second bit of historical, that I want to, the second historical question that I want to add was the name of Mark Kac. Mark Kac sort of brought this sort of spectral question to mathematics, and today this question is a prototype for many of the questions that arise in spectral theory. Can one hear the shape of a drum? Actually, I'm always whenever I modeled a number of things on Mark Kac, and so whenever I say something, I always like to say something about him. It turns out Kac was Polish. He was born in 1914 in the town of Krzymanich. Krzymanich was then in Russia, and then later it was in Poland, and now it's part of Ukraine. And he in his memoir he writes in a memoir about Kac, someone wrote. He was fond of Poincaré's distinction between God-given and man-made problems, and he was particularly skillful at pruning away superfluous details from problems he considered to be of the first kind, leaving the question in the simplest, interesting form. And it said that he mistrusted as insufficiently digested anything that required fancy technical machinery, to the extent that he would sometimes insist on clumsy but elementary methods. And I often think, as a way of teaching mathematics, this is a really excellent model. Sometimes one should be mildly distrustful of sort of fancy technical things, even though they're quite useful. And in seeking an understanding, one should find them in at times sort of clumsy elementary methods. So Kac's question really sort of revolves around, can we hear the shape of a drum? Given the shape, what can we infer about the sound? And given the sound, can we reconstruct the shape? And really in mathematics, to consider this question, we imagine some region D in the Euclidean plane, for example, the interior of an octagon. And suppose that, a drum head is fashioned in the shape of this region D. If we knew all of the frequencies that such a drumhead can emit, could we infer the shape of D? And broadly, spectral geometry is the study of how the geometry of an object is related to the natural frequencies at which this object can vibrate. And in mathematics, the natural frequencies of an object are given by the eigenvalues of a partial differential operator called the Laplacian. And these eigenvalues form an infinite sequence of numbers that tend to infinity, which we call the spectrum. And at some level, the correspondences that we have identified, sort of couched in the language of drums, are essentially saying that two different types of drums of radically different character make almost the same sound. So that's the way that I, explained to my mom sort of what I'm doing, and it's always a good way to start a talk in that way. So the basic outline. So what we have is a quaternion algebra. So perhaps let's see whether or not this actually works now. So basic outline. So I have here a quaternion algebra. Quaternion algebra. I have an order in the quaternion algebra. And from this order, what I'm going to do is I'm going to form two arithmetic function groups. Okay. And then I'm going to look at the Riemann surfaces that are formed when those groups act on the upper half plane. The critical sort of issue here is that O1 is a co-compact arithmetic Fuchsian group, and gamma 0D is a hecacongruence group. It's not compact, but it's cofinite arithmetic Fuchsian group. And so these groups act on the upper half plane, and essentially what we are, so O1, sort of the group of units in an order O, so clear. O1 sort of group of units in an order O, gamma 0D and SL2Z, hecacongruence group of level D, H point away half plane. We act on the upper half plane, so O1 \H and gamma 0D \H are respective compact and finite volume non-compact Riemann surfaces, right? So that's what I mean about the radically different character. One drum is compact in some sense, and the other is non-compact, but cofinite, finite volume. And so what we're doing is we want to relate the spectral resolution of the hyperbolic Laplace operator delta on L2 of O1 \H to that of the operator on L2 of gamma 0D \H. And so we do this in the case of mass waveforms. We want to do this by using the classical Selbert trace formula. So that's the broad outline of what we've been doing. So maybe just to clarify things, the correspondence that we're interested in. We have a quaternion algebra. We have orders in the quaternion algebra. So this quaternion algebra has something called a discriminant, and this is the way in which discriminant. Right. And so this discriminant D is precisely the D that is used for the D that gives the level of the hecacongruence group, right? So quaternion algebras, we take a particular order in the quaternion algebra. Inside of that order, we look at the group of units in that order. That order has a discriminant, and so we associate the discriminant D with the level of the hecacongruence group. And on that order, as I've just described, we can think of mass forms on the mass forms on that correspond to the Fuchsian group, the compact Fuchsian group O1, and we can think of mass forms on the hecacongruence group gamma 0D. And so we look at these spaces of mass forms on the respective co-compact and non-co-compact but cofinite groups. And the Jacquier-Langlands correspondence asserts that there is a relationship between these two sort of spaces, and the way in which we will establish that relationship is by way of the Selbert trace formula. So in a nutshell, you sort of have the picture of what I'm doing, and then now I need to sort of maybe make that picture a little more precise. So in order to make that picture a bit more precise, what I want to do is I want to go to what drove this process. So there's a paper called Asymptotic Densities of Mass New Forms by Morten Riesager. And in that paper, sort of Riesager investigates the asymptotic behavior of n gamma 0. So he investigates sort of n gamma 0 d nu lambda, right? And I'll have to say what that is. But he investigates this as a spectral counting function of Laplace eigenvalues for mass new forms on gamma 0n. And he asks this question for which hecacongruence groups gamma 0m is the spectral counting function of something called co-compact type, and I will say what this is in a moment. And the specific issues, for what values of D, as I've written here, will this spectral counting function exhibit asymptotic behavior that is characteristic of that of a spectral counting function of a co-compact arithmetic Fuchsian group. And so the idea, I have a cofinite arithmetic Fuchsian group, and as I described before, so I wrote gamma C to indicate that co-compact, and gamma 0D, non-co-compact, but cofinite. So the automorphic Laplacian related to gamma. And so n gamma lambda is the number of lambdas less than lambda, such that lambda n is in the spectrum. So it counts the number of spectral elements up to some particular point. Right? And what Riesager discovered, so I went to clear. What Riesager discovered was that in the case of a co-compact group, the spectral counting function has an asymptotic expansion of the form, a volume of O1 backslash h over 4 pi, so something related to sort of the area, and its error term was of the order of the square root of lambda over log lambda. So what I want to draw your attention to is if I'm looking at the spectral counting function for a co-compact group, then the error term is of the order of square root of lambda over log lambda. And when I'm looking at the asymptotic expansion spectral counting function for a Hecke-congruence group, then the error term is of the order of the square root of lambda times log lambda. And so I want to draw so when it's co-compact, the error term is of the order of the square root of lambda over log lambda. And when it's non-co-compact but cofinite, then the error term is of the order of the square root of lambda times log lambda. And what Riesager discovered was that I need to make some definition. I guess time is sort of running against me. I would need to make some definition about sort of what I mean by new forms, but you can imagine that by new forms, loosely, I mean, so I have forms on a group and forms on a sort of subgroup. And so the idea that the forms that are the forms on the sort of subgroup that are native to the subgroup, that don't derive from the group that contains it. So what Riesager discovered was that for some Hecke-congruence groups, if you counted only the new forms, only the eigenvalues corresponding to the new forms, well, when D was a product of an even number of different primes, that the new form asymptotic expansion the new form asymptotic expansion for a Hecke-congruence group looked very much like the asymptotic expansion for a co-compact group. And so the question is, how do you sort of explain that? And so what we tried to do was to say, well, okay, can we find some explicit relationship between this Hecke-congruence group and some specific co-compact group that is sitting in some quaternion algebra someplace? And so this is broadly the correspondence that we're establishing. And here's the theorem that Riesager presented for us. And this is where I get the gamma 012 new lambda. So Riesager sort of proved the following theorem in his paper. So take M, N, and T, natural numbers defined uniquely by the requirements that N is square free and M has the form NT squared. And so he proved that N gamma 0 M new, so the spectral counting function of new forms on gamma 0 M is of co-compact type if and only if at least one of the following things holds, like N contains at least 2 primes, and n is a prime, and 4 exactly divides n. And you can see now where my n gamma 0 12 new lambda is coming from, right? So thinking of 12 as 4, and then our prime, n is a prime, so n 3, and our prime 2 squared 4. And so what it turns out is that we know that based on Resager, that n gamma 0 12 new lambda is of co-compact type, and the issue then is to sort of say, is there some unit group in a quaternion algebra whose spectrum will correspond to some aspect of this spectrum in gamma 0 12? And broadly, what we've been able to say is that such a thing is true. I'm just looking at the time, and okay, so mindful of let me just say 2 more things, and I'll just I'm sorry. Sometimes you prepare more to say than you should. So how is this sort of broadly explained? So that we have this correspondence between spaces of automorphic forms for co-compact, that is compact quotient space gamma C, and non-co-compact but co-finite arithmetic Fuchsian groups. The Jacquier-Langlands correspondence is the thing that tells us that there must be this. It tells us that to any non-constant eigenfunction of the Laplacian on a co-compact arithmetic Fuchsian group, there should correspond a non-trivial cost form with the same eigenvalue on some non-co-compact but co-finite arithmetic Fuchsian group. So what we have been trying to do is we know by way of the Jacquier-Langlands correspondence that there should be a relationship. And what we've essentially been doing is sort of looking for these relationships in various places. And then once you have candidates for these relationships, the way you're going to establish that those candidates are precisely what you need is by way of some sieving with the Selberg trace formula. And so I'm just going to quickly sort of say, I'm going to skip some of the results, and I'm going to say about the last result. What we've been able to prove is that there are some particular orders that establish that there is a real nice bijection between a set of unit groups in particular Quaternion algebras and their associated Hecke-Congress groups. And we've also been able to establish that there are, even within Quaternion algebras of particular types, that one can establish these spectral correspondences. So this was something that was not known. Before. What we still are left with is there is still a situation where, when we have n being 4 times a prime times u squared, where p is a prime, u is odd, we have not been able to find a quaternion order with a natural correspondence between new forms as Resager has described. What we suspect is that there are none, but we have not been able to prove that. Also, and so perhaps that's probably a place where I realize my time has expired. So maybe just one last for those of you who've never seen this before, what does the strategy? So what we do is we compare Selberg sort of trace formulas. We look at the identity term, the elliptic term, the hyperbolic term, and we look at sort of special linear combinations of trace formulas and show that these things kind of align. There's a notion of local embedding numbers which allow us to really establish it is this sort of agreement on these local embedding numbers that really sort of gives us the correspondence. What I'll do is I'll put a link to the paper in the chat, and you know, we can offline as you see appropriate kind of have a conversation. So I'll say thank you here and pause. Thank you. And I'll just do this.
Okay. All right, great talk, Terrence. Does anyone have any quick questions?
Yeah. Can I ask something?
Yeah,
yes, you can.
Yeah,
yes.
Terrence, in the beginning you mentioned like from the spectrum you're able to determine the shape. That's really interesting. Can you just comment a little bit more on it? Like if you're, not just a drum but any other instrument, would you be able to...
Yeah, so there is some work by Woolpert and Webb that show how you can so the question is, can you hear the shape of a drum? And the answer is yes. In some ways, the work of Woolpert and Webb kind of establish some techniques by which you can do that. And there are other techniques that are known, sort of Milner sort of ways in which you can look at some manifolds. Yeah, so there is some work, and I can send some links to those also.
I mean, can you generalize this to any type of vibrating shape?
No, I don't think you can, but there are some. There are some manifolds where you can do this.
Yeah, because some time ago I looked into the spectral forms with the map functions and so forth. We wrote some papers on it, but slightly different. Any other groups that you use in here?
No, so I've just been focused on the Hecacongress groups and the unit groups that come from the orders in the Quaternion algebra. And so for us, the idea is to sort of figure out, you know, given the arithmetic, to sort of figure out what kinds of orders would be the best candidates for establishing the correspondence. And then once we kind of have a sense of what that order might be, then kind of working through the details of the linear
correspondence.
The linear correspondence, yes, the linear combinations of the trace formulas to see whether or not it works out.
Yeah, it looks like in your last slide there's some hints towards it.
Yes.
Going from 615 to, you know, and on in your very last slide. So it looks very nice.
Yes.
Might be a nice thing to work out. Yeah.
Yeah. I mean, it is. I mean, you know, the point is, you know, I indicated to some discussions about the Selbert trace formula, which I'm sure many. Yeah. So, you know, you have these spectral terms which come from the discrete and continuous spectrum of the automorphic Laplacian on the group. And then you have these geometric terms that are sort of integral operators that depend on the conjugacy classes in the group. And the Selbert trace formula for these co-compact groups and the Hecacongress groups are already well known. So we need just two versions, one for the co-compact group and the other for the Hecacongress group. And these are both known. And so, you know, I'll skip some of the details, but so the way that you know, you can view the sort of like, there's an identity component, there's an elliptic component, there's a hyperbolic component in the case when things are co-compact, and in the case when things are non-co-compact, you have, you know, an identity component, an elliptic component, hyperbolic component, and a parabolic component. And so the thing is, if you get the linear combinations right, what can happen is that this parabolic component goes away, and it mimics exactly what one would expect for the right co-compact group, and so that's been the essence of what we've done. Yeah.
Okay, nice.
Yeah, very nice. Okay, Terrence, if our audience has more questions, can they email you?
Yes, certainly. And what I'll do is I'll just stick a link to the paper in the chat, so that way you know, folks can take a look and, you know, send questions as appropriate.
Okay, great. Thank you, Terrence.
Thank you.
Okay.
I want to give a quick overview of the calculus over quaternion algebra. Since statements of calculus are based on statements of linear algebra, I will start from some definition of linear map. I also use notation 1.1 for the image of the map F. Linear map of algebra A over commutative ring D satisfy two equalities 1.2 and 1.3, where A and B belongs to algebra A and D belongs to commutative ring D. Also, I use notation L, D, A into A for the set of linear map of the algebra A. Now, let the product in algebra integer square of quaternion algebra be defined according to the rule 1.4. We see that here a different order than here. A representation of tensor square of quaternion algebra in the set of linear maps of quaternion algebra defined by equality 1.6 is left module over tensor square of quaternion algebra. Here's I put attention that map G I put instead of symbol of tensor square of tensor product. The map, yes. If we put G is identity map, then we can identify linear map of quaternion algebra with tensor 1.7 using the equality 1.8. Here I have some over index S expression f as 0 and f as 1 in the equality 1.7 is called component of the linear map F. However, from the equality 1.9, we see that in different expression, but in the same tensor, it follows that the representation 1.7 of the linear map F is not unique. So I use little bit different definition. Let 1 I, G, K be basis of quaternion algebra H. The standard representation of the linear map 1.10 defined by equality 1.11 is unique. How I get it? Because in this representation, FSP can be represented as this way. Then summarize all together, I get quaternion Fig. This quaternion Fig in the equality 1.10 is called standard component of linear map. Choose between a standard representation or a regular representation depends on the problem that I need to solve. The same way as a linear map, I can introduce polylinear map, assuming that this map is linear with respect to each argument. I also use notation 2.1 for the parity of permutation. A polylinear map F is called skew-symmetric if it satisfies equality 2.2 for any permutation sigma. I use such notation for permutation instead of sigma I1, sigma AN, because it's more compact. Let F be polylinear map. The map 2.3 is called alternation of polylinear map F. So I have here some Sn is the set of all permutation of the set of variables A1, AN. Also, I use definition 2.4 and 2.5. The map omega from open set U to the set of polylinear skew-symmetric polylinear maps is called differential form. And if I have p-arguments, I tell that this is form of degree P or P form. From theorem above, it follows theorems that differential one form in quaternion algebra can be represented by equality to that 6, and its value is defined by equality to that 7. So I put A, quaternion A, instead of tensor product. Similarly, if I want to use standard representation, that I have representation to that 8, and its value will be defined by equality to that 9. The map F of quaternion algebra is called differentiable on the set U if there exists differential form df over the x such that increment of the map F is defined by equality 3.1, where the map O satisfies to equality 3.2. Linear map df of x over the x is called derivative of map F, and the differential of the map F is defined by equality 3.3. Also, it's easy to show that definition of derivative is equivalent to standard definition 3.4. No, because derivative is one form, then we can tell that derivative can be represented that inequality 3.5, and correspondingly differential can be represented like inequality 3.6. This coefficients is called component of derivative. Also can use standard representation of derivative by equality 3.7, and this coefficients is called standard component of derivative. From definition 3.4 of derivative, it's easy to show that derivative of the map y equal x is identity map. Also, the same way, I can show the derivative of the map y equal x square has form of two terms, and its differential has form x dx plus dx x. Now we see here components of derivatives. Let f and g be differentiable map. The derivative of their product satisfy to equality 3.14. No, it's a standard theorem, but here is very important order of the functions. From this theorem and from the equality 3.8 and 3.10, it's easy to show the derivative of function y equal x cubed is defined by equality 3.15, and its differential is defined by equality 3.16. Because derivative is belongs to the set of linear maps of quaternion algebra, then we may consider the equation if map df of x over the x is differentiable. So let derivative df over the x of quaternion algebra is differentiable on the set U. The differential to form d to f over the x twice, defined by equality 4.1, is called derivative of second order of map F. Like derivative of the first order, we can represent the same way derivative of the second order, but here we have tensor of the order 3. And this coefficient is called component of the derivative. let the derivative of second order of the map be continuous. Then the second derivative is symmetric bilinear map. It's a very important theorem. Let me have derivative of any order n of order n minus 1 of the map. The same way as we define derivative of the second order, by induction, we can define derivative of the order n by equality 4.5. In particular, we also assume the derivative of order 0 is map itself. If map f has derivatives under order n, then the polynomial 4.6 is good approximation for the map f. If map f has derivative of any order, then passing to the limit n to infinity, we get expansion into series 4.7, which is called Taylor series. We return to differential forms. Let omega be differential form of order p. Then expression 4.8 is called exterior differential of form omega. In particular, exterior differential of derivative of function f equals 0. Now we consider opposite operation. If we have one form omega, then this form is called integrable if there exists a map of quaternion algebra such that derivative of the map f is differential form omega. Then we use notation 5.1, and the map f is called indefinite integral of the differential form omega. From a theorem that we considered above, we see that integral 5.2 is x squared plus c. This integral can be written also in the form 5.3. And also we see that integral 5.4 is x cubed plus c. And also this can be written in the form. Here we put the x instead of tensor product, we have the x. Here x dx x, and here x squared dx. So it's this way. It may be impression, at least I have initially such impression, that there is some kind of symmetry which is enough to make sure that differential form will be integrable. But this is not the case. For instance, differential form 3x times x is not integrable. Let U be open set. Differential form omega is integrable if and only if its exterior differential equals 0. Now we consider path gamma in the open set U, and we define integral of the differential one form omega along the path gamma by equality 6.1. Integrand is here is written according to the chain rule. No, it's a familiar theorem from real numbers. Let gamma be path on the set U and f be differentiable map. Then integral of df along the path gamma is defined by equality 6.2. Let U be open set. The following properties of differential form omega are equivalent. Omega is integrable in U, and integral of omega along any loop gamma equals 0. And from this statement follows the definition 6.4. Let U be open connected set. and differential form omega be integrable. For any quaternions A and B, we define definite integral by equality 6.3 for any path gamma from A to B, because this integral does not depend on the path. Below, we initially considered tensor representation of linear map. I want to show that there is one more interesting representation of linear map. I can introduce map of conjugation 7.1, 7.2, 7.3, and 7.4. Here I make change sign for only one variable, I, G, K. Map of conjugation have standard representation 7.5 until 7.8. Also, I introduce operation bullet by equality 7.9. And this operation, it's defined by equality 7.10 also. And this map is endomorphism of a set of linear map of the algebra A. And representation of algebra A in the set of linear maps defined by equality 7.13 is left the model over algebra A. In particular, this will be true for quaternion algebra. Now, if any map F, I may consider as map of variable x0, x1, x3, and this linear map. If each linear map has a matrix F(G), if I consider quaternions from each row, form from each row of this matrix, this way, then map F has expansion with respect to map of conjugation. It's very interesting to put attention to the first term. It's similar to the complex number theorem. And also, if map, I consider any map of algebra, of quaternion algebra, and get expansion x equal x0 plus x1 plus x3 k, then and map F is differentiable, then it has partial derivatives which form from each matrix of Jacobi matrix. And then derivative of the map F has a representation 720 using its derivatives. For me, it's very important that this coefficient is similar to the left side of Cauchy-Riemann-Futter equation. This representation is good for some application, but I just want to show how it looks derivative of x squared using this representation. This here x star is conjugate of x, so it's a little bit different from formula that we saw above. Now that's all that I want to tell. I uploaded this to your website, and in Appendix A, I give some additional theorem that people can look if they're interested.
Thank you.
Can I ask a question?
Yes. Yes, please do. Please go ahead with questions.
Okay, thanks a lot. what you show like practically on your last slide is like similar to the something that we've seen as a Maxwellian tensor in the D equals 4 counterpart of the so-called Sugawara-Sommerfeld connections. I don't know if you're familiar with those. I think these are very useful, and this matrix representations, and then they're also shown in there.
Yeah, this equation is very important because it relates to theory of integration, and
right.
It was developed from a request that free form is differentiable.
Right.
But for me, it's interesting that I get this equation a little different way, and also for years a long time I tried to find analog tensor representation, but it's looked little bit no, I didn't like this representation. But what is interesting there, that it looks like the F here will be a circle. I can put right here a regular derivative, and it looks like it can be a little bit generalized, but I not find a way to find answer to this question. I hope that I will find later on. And when I was prepared this talk, I put attention for this type of representation one time more, and probably this will be where I can find some interesting solution in this direction as well.
Yeah, thank you.
Does anyone else have any other questions?
Yes, I am back.
Oh, very good. Johannes, you have a question for our speaker?
Not right now. I will think about a question now that I've been spending a lot of time trying to fix my internet. Right.
Okay.
Okay. All right. So does anyone else have any questions about our last speaker? Speakers?
Maybe I'll have one more question if that's okay.
Great.
Yes, please go ahead.
What about Filter's quaternion analysis and applications into that, into Filter's work?
Filters?
Yeah.
But I'm not sure about this definition. What do you mean filters?
I mean, the quaternionic function theory was built at some point by Filter, and I'm wondering, like, if you have any applications of
probably I need to find out, because I hear this definition today first time. Sorry, but I will look. If I find something interesting and can apply it, that will be fine.
Yeah, because on the applications of these to the complex analytic functions, there are all types of mishmashes. So I was wondering if you had any comments on that.
Certainly, it has a lot of applications.
Yeah. Like the Weierstrass power expansions and so forth are all related to, probably.
You can contact me by email, and probably we will be able to discuss this in the future.
Okay, I'll send you an email. Thank you.
Yeah, thank you. I appreciate it. Thank you very much.
To talk to us about twists on quaternion algebras and related orbitals. And so you can start, I guess, in 1 minute.
Sure.
You want to be like exactly on time.
Yeah. Oh, no, thank you very much. So, yeah, I guess now I can take over for a while until my internet decides to do an outage again. Right. I was on my other computer for a little while using the schoolhouse next door, but I couldn't do audio with that. So I could hear, but I couldn't speak. So thank you very much, Senya. Did I get it right now?
Yes.
Okay, Senya, thank you for coming to our special session. And as My colleague Chris mentions you're going to be speaking on twists on quaternion, algebras, and related orbifolds.
All right. Thank you.
Okay, so I think it's time to start.
Yeah, it's 12:30 on my
Right,
clock,
exactly,
so.
according to my clock, which works.
So thank you very much for inviting me. What I'll be talking about is involutions on quaternion algebras and how you can construct interesting geometric objects from these. So before I get into that, let's do something a little bit simpler. So recall the modular group, right? This is defined as SL2Z. This acts on the hyperbolic plane, which we imagine as the upper half space. It acts on it by linear fractional transformations, right? If you have a matrix A, B, C, D acting on some complex number Z, then that gets sent to AZ plus B over CZ plus D. And these turn out to be hyperbolic isometries. And there's nice consequences of this. You know, you can construct a related geometric object called an orbifold by just quotienting out by the action of gamma, right? And you can visualize this by taking a fundamental domain of gamma and gluing sides together. And this gives you something that's not quite a manifold, because there's a finite collection of points where it doesn't quite look like a plane, but rather it has corners. So we say it's an orbifold because there's this finite collection of points where you have to do a little bit of machinery in order to flatten out if you want. We can do something a little bit more complicated, a dimension up. So take K to be some imaginary quadratic field like Q joint square root minus 2. Take O of K to be its ring of integers. So that would be Z joint square root minus 2. Then again, we can take the special linear group SL2OK. This is usually called the Bianchi group. This now has an action on hyperbolic 3 space, which again, we think of as the upper half space. And this action can be described in a very nice way in terms of quaternions, where what do? Well, you think of H3 as consisting of all quaternions with no K component and positive J component. And then you can define the action simply by linear fractional transformations again, without any change whatsoever. Things are just a little bit less commutative now than they were before. And just as before, you can construct an orbifold. You can say, well, you know, I can quotient out by the action of this group. And this gives you some nice geometric object. And there's very nice consequences to thinking about it this way, because it gives you a sort of dictionary between the algebraic properties of the ring on one side and the geometric topological properties of the orbifold on the other side. So for example, the isomorphism class of the ring exactly gives you the homotopy class of the orbifold, which happens to be the isometry class. The fact that these rings of integers are maximal among orders basically tells you that the orbifolds are minimal in some sense. They have minimal volumes in terms of some class of arithmetic orbifolds that you can define. The class number of the ring of integers is exactly equal to the number of cusps of the orbifold, the number of places where it sort of stretches out to infinity, right? The discriminant of the ring gives you a way to easily compute the volume of the orbifold. And if you have a Euclidean algorithm defined on your ring, then you can turn this into an easy algorithm to compute a nice fundamental domain for the orbifold. Something called the Dirichlet domain. And all of this generalizes. In fact, there's a general theory that matches orders of quaternion algebras and arithmetic 3 orbifolds. I will not go into this here, but it is something that exists. And now the question that's been of interest to me for the past few years is, why can't we extend this further? Or can we extend this further? Like, say, can we do something similar for hyperbolic 4 space? Right? So what we'd like to do is find some nice arithmetic subgroups of the isometry group of hyperbolic 4 space in such a way that it would allow us to relate some kind of algebraic invariance on one side to geometric topological invariance on the other side. That's sort of what we'd like. And it might not be obvious that there should be any obstructions to this. Like, why shouldn't there be a general theory of this? It's not quite so easy, because there is something very special about the 2- and 3-dimensional case, because there are accidental isomorphisms. PSL2R happens to be isomorphic to SO plus 2,1, which is the orientation preserving isometry group of H2. And PSL2C happens to be isomorphic to SO plus 3,1, which is the orientation preserving isometry group of H3. But these are accidental isomorphisms. They don't scale, so to speak, right? In the theory of Lie groups, you have isomorphisms, you have families of Lie groups, and for sort of low dimensions, some of them happen to be isomorphic, but as you go up, they're no longer isomorphic. And so if you want to do something similar, then you have to find some sort of new accidental isomorphism with SO plus 4,1. So how do we do that? Well, this is where rings with involutions come in. So briefly, right? So suppose I have some ring R. What do I mean by when I say, what is an involution on it? Well, it should be some map sigma from R to R, which should preserve addition in the sense that sigma of x plus y should be sigma x plus sigma y. It should reverse multiplication in that sigma xy should be sigma y times sigma x. And it should square to the identity. So if I apply it twice, then I get back to where I was before. And you can build up a nice, category of these things if you like. You could talk about morphisms of rings with involution, and all that will be is, it's just a ring homomorphism which commutes with the relevant involutions. We will not need that here. Let me instead give some examples of rings with involutions, so you have something to hang on to. So the most trivial example that I can give you, of course, is that if R is a commutative ring, then the identity map gives you an involution. This is not a very interesting example. Here's a slightly more relevant one to our interests, which is take the Hamilton quaternions, which I will write as H sub R. Take your quaternion x plus yi plus zj plus tk, and just switch the sign of the k component. This, as it turns out, is an involution, which will be very important to us later. So burn that one into your mind. Here's another interesting example. Let's suppose that I have a commutative ring and I look at the 2x2 matrix algebra. Then I have an involution called the adjugate, where what does it do? It takes a matrix A, B, C, D and sends it to D minus B minus CA. This is, of course, related to the determinant. If R is not commutative, then this will fail to be an involution. But it turns out that there's a way to save this, which is that if you start with an involution on your ring, so you have a ring R with an involution sigma on it, even if R is non-commutative, you can build a new involution on this 2x2 matrix algebra as follows. You define this induced involution, sigma hat. And what does it do? Well, it does the adjugate map, but it also applies sigma to every single coordinate. And the funny thing is that neither of those transformations by themselves is an involution. But if you put them together, then they sort of cancel out the problems of each of them individually. And this induced involution is quite interesting because it allows us to define something which I've termed the twisted special linear group. So here's how this works, right? You start with some ring R with involution sigma, and now you define this special linear group SL2R, but twisted by sigma. That's what the superscript there means. And what does this mean? Well, it consists of all M in this matrix algebra, such that the induced involution gives you the inverse, meaning that M sigma hat of M is equal to sigma hat of M. M is equal to 1, the identity. And it's, you can easily check that this is a group. And why do I call it this twisted special linear group? Well, here's the most obvious example of such a thing. If R is a commutative ring, then you can take the involution to be the identity, and then it's easy to check that SL id to R is just SL to R. So in other words, if the twist is trivial, then you just recover the usual special linear group. If the twist is non-trivial, then you can get all sorts of other new interesting groups. There's all sorts of symplectic groups that you can get in this way. But the example that is interesting to us, if we're interested in quaternions, is the following. So take H sub R to be the usual Hamiltonian quaternions. Take double dagger to be this map that flips the sign of the K component. Then SL double dagger to HR, if you quotient out by plus or minus 1, happens to be isomorphic to SO plus for 1, the orientation preserving isometry group of H4. And this example is not exactly new. So Wahlen wrote it down in the early 1900s, although he did not, he formulated it very differently. He did not talk about rings with involution at all. That's my own sort of reformulation of that work. But in any case, how does this work? How does this isomorphism work? How does the action on H4 work? Well, here's what you do. You think of hyperbolic force space as consisting of all quaternions with positive K component. And then you act by Mobius transformations. Exactly as you did before, no changes, just things are even less commutative than they were previously. But otherwise, this works exactly the same, and this gives you the desired action. So it's sort of this very beautiful thing. If you're interested in learning more about how you can represent isometries of hyperbolic space in terms of Mobius transformations, there's some very nice papers by not by Wahlen, by Alfors, who took early work of Wahlen and sort of tried to popularize it, and he gave this nice description in arbitrary dimension in terms of Clifford algebras, which is very interesting, but sadly I don't have time to talk about it. In any case, getting back to our original question, we want to find nice arithmetic subgroups of this. What should we choose? Well, we're going to try and mimic what we did for the modular group and for the Bianchi groups. And what we did there is we started with some R algebra, and then we passed to some discrete subring of it. So for example, we started with the real numbers R, and we passed to Z. Or we started with C, and we passed to some ring of integers of an imaginary quadratic field, like Z joint square minus 2. And here we can do the same sort of thing. The only trick is that we can't just consider discrete subrings. We have to consider discrete subrings with involution, because we have this extra algebraic structure on our thing. It's not just that we care about the Hamilton quaternions, we care about Hamiltonian quaternions with this choice of involution. So we have to respect that substructure. And so here's an example of such a thing. So this is a ring O, which consists of all linear integer combinations of 1 plus I squared 6j all over 2, and square root 6j plus square root 6k all over 2. This is very obviously closed under addition, but you can also check that it is closed under multiplication and that it is closed under the involution. I do have an extra I in there in the middle coordinate I just noticed, so that's a mistake, but hopefully you will forgive me that. And sort of just as before, we say that such a substructure is maximal if it's not properly contained inside any larger discrete subring with involution. And again, there's a nice theory about when do you determine whether something like this is maximal. This was the first paper that I published, I believe, but again, don't have time to talk about it, which is so sad, but what are you going to do? But in any case, here's really the meat of the matter, is that just as before, you had a nice dictionary between the algebra on one side and the geometry and topology on the other side. Same thing happens once again. On the left-hand side, you have your subring with involution O. On the right-hand side, you have an orbifold defined by starting with hyperbolic 4 space and quotienting out by the action of this group, SL double dagger 2O. And now we can relate number theory on one side, geometry on the other. So for example, the isomorphism class of the 2x2 matrix group of O with this induced involution exactly corresponds to the homotopy class of the orbifold. The maximality among orders with involution of O relates to the fact that the corresponding orbifolds are, again, in some sense, minimal volume. The class number of O is exactly equal to the number of cusps of the orbifold. And there's this analog of the Euclidean algorithm. It's this twisted Euclidean algorithm, which you can define for some of these rings O. And if you can, then it translates into an easy algorithm to compute a fundamental domain for the orbifold. The one thing that is missing in this table, sadly, and I was so hoping that I would manage to get it done by today, but I didn't manage quite to do it, which is that it should be possible to compute the volume of the orbifold in terms of the discriminant of the ring. So when I was a kid, I was a big fan of choose your own adventure books, and Goosebumps, as I remember, had quite a few of them. Now, why do I say this? I really wish that I had the time to go through every single one of these things and tell you all about how they are proved. But time does not permit me this. So we shall do a choose your own lecture. So at this point, I'm going to pause. And if anyone has any questions, please ask them. But also, if there is anything on this list that you look at and you think, oh, well, I'd really very much like to hear more about that, please say that, and I will be very happy to say more.
Okay, well, I have a question. Can you go back to your first slide?
Yes, this one?
Oh, no, next one. One after, yeah. No, one after.
This one.
No, I think I missed it. Yeah, anyway. Oh, yeah, okay, right here. Did you look into like a PSL 2, H quaternions instead of the real and complex part going into SO51?
Right.
Which is really interesting for us, especially doing string theories on or M theory actually is allowing us to move through SO91s, which contains the SO51 internally. The higher one goes actually into the octonionic mode, building the superstrings and dimensions. So I'm just wondering if you did some more work on the quaternionic part.
Right. So I don't have anything published which talks about SO plus 5.1.
Right.
That said, I believe that a lot of the arguments that I use can be done there as well, with some modification. I mean, the reason why I started looking at hyperbolic 4 orbifolds in the first place was because I started out working with integral crystallographic sphere packings, which, as it turns out, are the limit sets of hyperbolic 4 orbifolds. And so that's why, you know, perhaps in another universe where I started in from the hyperbolic isometry group side, I might have skipped over 4 and just gone for 5-dimensional things, and probably that would have made my life easier. But that's not how it happened. So there is a paper that I'm working on now which treats SO 3.1, 4.1, and 5.1 on roughly equal footing. I have no idea when that paper will be finished, but at that point I'll be able to say that, yes, I do have something published that treats that case as well.
Yes, these things do come up in strength. He's right. Yeah, I've heard about this. Yeah, thank you.
Yeah, what's really interesting for us is really basically SO10.
Yes, that's right. That's right. Yes, I remember reading about this.
As far as your question went, I'm interested in learning about the connection between class numbers and number of cusps.
Ah,
okay.
Sure, absolutely. So the funny thing is that the argument is very, very similar to the classical one. So first of all, what do I even mean by the class number when we talk about quaternions? So you can't quite get a class group is the problem, because everything's non-commutative. But you can get a left class set and a right class set, but it turns out to be basically identical. But if you allow yourself to get rid of the fact that you don't have a group structure anymore, then you can still define a set as in the same way. It's, you know, equivalence classes of invertible left O ideals modulo some right right multiplication by units. And so then you just define class number as the number of elements in this class set. And this is always finite. And this is unpublished, but there's just this nice map as it happens. This nice well-defined bijection between the rational points of H. So H plus here is quaternions with no K components. Let's make this simple. Together with this point at infinity. So this is the boundary. So this is the rational point on the boundary of hyperbolic four space, right? If you quotient that out by the action of this group, then you get a map into the left class set. And it's basically, it's the same thing as before, which is, what do? Well, anything in here, any of these rational elements on the left-hand side can be written in the form x, y inverse. And then you just map that to the O ideal generated by x and y. There's exactly one problem with this, which is that xy inverse has to lie inside of this special restricted set H plus. So you need to show that every ideal on the right-hand side can be represented by two elements of this special form. That's like the one tricky part of the proof, really. And you do that, it's some argument considering ternary quadratic forms is really what it is. But yeah, once you know that you have this bijection, well, that immediately tells you, oh, well, on the left-hand side, what are you looking at? Well, you're looking at cusps of this orbifold. And on the left-hand side, you have the class number. And so since there is this bijection, the two have to be equal. In terms of how do you prove that this is a bijection, so surjectivity, you have to prove something about how these left ideals can be generated. In terms of proving that this is injective, the easiest way to do it is to realize that, oh, well, the SL double dagger 2H, so H is the quaternion algebra that contains your order, that acts transitively on the fibers. And so that just means that it's really just enough to consider the fiber over the trivial ideal. And there, the problem is easy. you just explicitly construct the matrix that will do it for you. So that's basically how that works.
So I wanted to ask about the discriminants, and so the two questions. So first, just an intuition about, you know, what is this map doing to the order, and then are the discriminants of the related orders? Is there a relationship between the discriminant of orders that are related by this map?
So which map are you talking about? So is this discriminant at volume or is this?
No, sorry, I'm thinking about the discriminants among themselves. Like so when you
see. So right. So the discriminant gives you an ideal that measures sort of I guess the volume of the fundamental parallelogram of this order. So the one way that you can think about it. This can be stated much more generally because you can do this over arbitrary algebraic number fields, but for Z, that's the right picture. And as such, if you have two orders, one contained in the other, well, their discriminants are going to be related by the, I guess, the square of the index of one and the other. Depending, I think, on how exactly you define the discriminant, because I think some people write it as always giving you a square, and some authors always say, oh, well, you should be taking the square root. So there's some things along those lines, exactly. So that changes exactly what the factors are, but that's the rough idea. Yeah.
Okay. So if I can ask one more question.
Sure. Well, if we have time.
For a 2x2 Hermitian matrices, you know, sometime earlier, where you put like alpha, beta, gamma, delta, and then the setting with a bar, and some of those containments are real. But what happens that in the so-called superstrings or classical string superstring theories, in dimensions 3, 4, 6, and 10 that we formulate them. In the dimension 3, you have O21 isomorphic to SL2R. In dimension 4, we have O31, which is SL2C isomorphic to. And then in 6 dimensions, we have O51. And I like to really see like how you can extend this so-called Lorentz transformations into the higher reality, maybe the Octonionic case, so that you can get like a general linear transformations and so on, which is completely undone. It would be very interesting for physicists to see such a structure to develop. I mean, I hope that you guys can go ahead and then go into this the higher reality for us, especially for 10 dimensions. It'll be really very nice to see. And because the problem with the non-associativity of octonions come in, and then you have to probably, you know, fix up some tricks. But what happens is that the automorphism group, the G2, that's built the lowest group by the octonions, might be, it's a 14 parameter group, which requires the associators in this expression. So in the 10 dimensions, you have 4 times 8 minus 1, which is what, 31 parameters that add up to the 45 parameters of O91, basically. And then, you know, that's with the inclusion of G2. And so that will be really something beautiful for us to actually see, to come into reality in terms of string theories. All right, so that's all I wanted to say. So if you have any comment on, you know, it will be.
I don't, and I fear that I'm out of time in any case. So, yeah. But once again, if I may end on this, thank you very much for inviting me to talk, and I will shut up now.